Okay, good afternoon. For those of you who don't know me, I'm John Kilner, and I'm one of the international PIs in the I²CNER program. And Professor Ishihara has asked me to chair this seminar this afternoon. So it's actually a great pleasure for me to introduce the speaker today, Dr. Jose Santiso. Santi and I have worked together on problems in oxide thin films for several years. In fact, I poached one of his best PhD students who now works in London with me, a young lady named Monica Buriel. So Santi is a PhD in physics, which he achieved from the Autonomous University of Barcelona, where he now works, and that was in 1993. His main interest has been in thin films, PLD, growth mechanisms, and characterization of thin film oxide materials. And I'd like to invite Santi now to give his seminar. I should have said, of course, that he works now in the Center for, let me put my glasses on and then I'll be able to read my notes. It's the Research Center for Nanoscience and Nanotechnology, which is currently called CIN2, isn't that right, Santi? And it's going to be changed to I²CNER, so it's nearly like I²CNER, which is I²CN, so we were very close to each other in acronyms. So Santi, if you come along and give us your seminar, Oxygen Surface Exchange Kinetics for Intermediate Temperature SOFC Applications.
Okay, so I did not know exactly which kind of talk I wanted to do here, and I decided to talk a little bit about one of the things that we are most interested in and related to solid oxide fuel cells, which is the oxygen surface exchange dynamics and the oxide materials, particularly for the application to intermediate temperature solid oxide fuel cells. And first, I will briefly show you the outline of my talk. I start with a brief introduction about why are we interested in this kind of intermediate temperature solid oxide fuel cells, why the surface exchange kinetics, and I will review some of the methods that are currently used for the measuring these surface exchange coefficients, and then I would explain more in detail some of the new methods that one can use now for analyzing these dynamics in the materials, particularly in thin films where I'm working in. And I would particularly speak about one technique that we are developing in our laboratory, which is related to time-resolved X-ray diffraction. I will show you more details about this. And a very new technique called Electrochemical Strain Microscopy, which is able to analyze at the local scale some of the features that we are interested in these materials. Finally, I will draw some conclusions about it. And our main motivation it's a common motivation in all solid oxide fuel cell community, is to reduce the working temperature of the devices, because this helps to have more durability of the devices, to reduce the cost of the device, and to be able to implement it at a larger scale. And our target is to work around 400, 500 degrees Celsius. And in the present technology, well, the one which is industrially implemented, it works at much higher temperature, above 800 degrees, around 900 degrees Celsius. And this is a real problem, but there are very different attempts to reduce this temperature, and most of our efforts are in this direction. But of course, when one tries to reduce the working temperature of these fuel cells, the fuel cells are a combination of different elements, mainly a cathode, electrolyte, and anode. And there are several works that have pointed out that the main limitation for the reduction of temperatures in these cells come in the cathode side. This does not mean that the electrolyte or the anode side have less importance. It's absolutely important to have better performance in all those elements and in the combination of all these three elements. But focusing onto the cathode side, what is given the limitations is the oxygen transfer from the gas phase. This is a sketch of this cathode part of the cell. So this is the electrolyte, and this is the gas phase containing the oxidant, the oxygen gas. So in the oxygen transport from the gas phase to the electrolyte, there are several steps, and one step is the oxygen gas reduction. So it's the conversion of the oxygen gas into oxygen ions, and for this you need, in this case, it's a typical cathode which has oxygen vacancies. So you need the oxygen vacancies, and you need electronic carriers to perform this reaction. So there are different steps that give the reaction rate, this reaction rate. But also there is once the oxygen ions incorporate into the cathode, they have to move to the migrate or diffuse to the electrolyte, and then it can have again some resistance, some barrier into the cathode electrolyte interface before it goes into the electrolyte. So there are different steps, but among all these steps, for instance, when one uses very thin films which are below 1 micron thickness, the diffusion path is very short. So the diffusion length is so fast that ionic diffusion is not the limiting step in this case. So the limiting step becomes the reaction itself. So it's mostly the surface exchange rate which becomes very, very important in these fuel cells. So, of course, there are several strategies to enhance this surface exchange rate. One is just a geometrical effect by enhancing the area, the effective area of the cathode. So this comes through control over the film morphology by building porous structures, for instance. But if one comes to the intrinsic kinetic properties of the material, so you need either to work in novel materials, new materials. So this is something that we are quite active in. But also, it's important in the surface state of these materials. So you need a control over the termination, which are the active sites on this surface. This is very critical. Sometimes if you have some anisotropic materials, you are interested in controlling the texture, the orientation of these crystals. So your termination comes to a particular plane, a termination plane. But of course, you can add some other materials, like an active layer, or you can put some islands of another material, which can be catalytically active. So those are the different approaches that we are using in our research. But of course, to compare all these figures, you need to be able to measure K in a proper way. And this is also difficult because it's very surface sensitive. And how do we measure this K rate, surface exchange rate in thin films? So there are very one can say classical methods, that some people here are specialized in some of them. And one of them is the use of oxygen isotope, oxygen 18, to use it as a tracer. It's called IEDP technique, Isotopic Exchange Depth Profiling. And the depth profiling is usually measured by secondary ion mass spectroscopy, SIMS. I give some details about it. There is another classical technique that is using the variations in the electronic conductivity and the electric conductivity of these materials, and by measuring the slight subtle difference in the conductivity, like it's called conductivity relaxation experiments. Those two are very classical. There are some techniques that have been developed very recently. There are some people here that they are specialized in these techniques, and I'm very happy to be here also to have a chat with Sean Bishop, who's recently published some works in this field, by measuring the optical absorption variations upon exposing this material to different atmospheres. So this is a very interesting method, and the one we have been developing in the last months, which is very close to this one, is trying to measure structure variations of the thin film materials in a dynamic way, so we can also follow very quickly the variations, the oxygen incorporation or the oxygen reduction, the film reduction in our materials. And also I would give some details about this electrochemical strain microscopy, which is an atomic force microscopy related technique that we are also working in. And I will describe briefly this first one, the isotopic exchange with oxygen 18. So the idea is to expose the material to an oxygen 18 enriched atmosphere, like in this case. So we have the surface of the film and the substrate, and we expose the material to the oxygen 18, and then it exchanges oxygen and self-diffuses the oxygen 18 into the material. So if we can control the time duration of the exposure and the temperature of the experiment, and then we freeze out this the composition profile after the experiment, we will be able to measure by SIMS the profile, so we can extract the values of where we only have to solve some equations for depending on the temperature and the time of the exposure. So we can extract the oxygen surface exchange, and in some cases the oxygen diffusion. We can do this in this classical experiment, but we can also do this in the same films, but in another configuration. So we protect the film with a gold layer, which prevents the exchange with the atmosphere, and then we do some openings into the film, and then we expose to the oxygen 18, so we allow the oxygen to get into the film from this side. Then if you have a single crystalline film, namely with the z-axis perpendicular or an AB axis horizontal, parallel to the substrate, then you can measure surface exchange and diffusion coefficient along a particular crystallographic direction. But with this configuration, you can measure in another crystalline direction. So with those two experiments, you can also obtain a profile, and then you can analyze this profile in the same way as before. Then you can measure if there is any kind of anisotropy in the oxygen diffusion and oxygen surface exchange in these materials. And we did that for lanthanum 2 nickel 04, which is a cathode material, which is one of these candidates as a cathode for low temperature applications. And we obtain, those are our results along the C-axis, perpendicular to the C-axis, parallel to the C-axis, and the results parallel to the AB axis. And we observe for the K, oxygen surface exchange, we observe an important anisotropy of about 2 orders of magnitude difference. So this is important because that means that for applications, we would need to texture these films in a particular way if we want to enhance the K values. But we are interested in the fundamental mechanism taking place in these materials, which give such a different surface exchange rate. And, well, we just remind these figures because we are going to compare with other techniques. It's the surface exchange rate along the C-axis of about 10 to the minus 9. And activation energies, it's a thermal activated process, so we can extract an activation energy, which is about 0.38 eV for this C-axis orientation. But also for the AB axis, as we said, we have 2 orders of magnitude difference, but we also have a difference in the activation energy, which means that the mechanism might be changing from one crystal orientation or the other. But then we can compare what happens with the other technique, the electrical conductivity relaxation. In this case, we take advantage of that the defect chemistry in this material, the oxygen species, the ionic defects are mainly oxygen interstitials in this material, but at the high oxygen pressures that we are working in, it's compensated by electronic charges, by electronic holes. So we have a direct relationship between the density of electronic carriers and the density of ionic species. So we can, and this depends very much on the oxygen pressure. So once we change the oxygen pressure, like we do here, so these are steps of the changes on the oxygen pressure, then we expect changes also in the density of carriers, of electronic carriers. So we expect conductivity variations in the material. So we measure continuously the resistance, the conductivity of the film upon changing gases, so we can switch from one gas line to the other. So we can observe dynamically how it approaches to the new value. And if the films are thin enough, this the main mechanism for this change in the conductivity is related to the surface exchange. Oxygen diffusion is almost not influencing this change, and it can normally be adjusted by a simple exponential decay or exponential increase, depending on the oxygen pressure change. And okay, this can be acquired very fast, so you can acquire millisecond variations. So this is very straightforward measurement. It gives you values which are averaged in the film. Of course, if you want to extract the intrinsic properties of your film, you need that the substrate is not conducting. So otherwise, if the substrate has some conductivity, it will be mixed and it will be difficult to separate. But it's something that we have to take into account, is that in these experiments we use metal contacts, typically silver or platinum contacts, and they can have some activity to the oxygen exchange. And if normally you don't protect these contacts, so the contacts are also exposed to to the gas phase, so they can have an influence. And this technique, one has to be very careful that is what you are measuring is not what happens in the contact. Otherwise, you have to protect them. And this is a simple profile, decay of the conductivity. And well, it's not very clear in this image. When you try to fit to a single exponential decay, it's not perfectly fit. So the best fit comes when you use a double exponential. And this is very common, very commonly observed in several groups that have been working with this technique. So these two exponentials have very different response time. One is fast, and the other one is a kind of 1 order of magnitude larger response time, so it's slower. So we normally say that the fast response is related to the real SOFC exchange, whereas the slow response, it might be related to an interface effect. Well, there's kind of different views of what could be this second slow process, but we believe that is something which is related to what happens in the interface with the substrate and the thin films. But of course, we don't know if by only these measurements, we don't know if it's something that it's a two-dimensional effect at the interface between the film and the substrate, or it's something that happens to the substrate conductivity, or is something which is in the film. So it's difficult to separate in this case. But what we see from the same type of films as we mentioned before for the lanthanum 2 nickel 04, we obtain a surface exchange reaction for this oxidation, which are of about 2 orders of magnitude much larger. So it means that maybe something is happening in the contact. So this seems to be much more active when using this experiment. But regarding the activation energies, they come more or less to the same values. We had 0.38 in the other case, and we had 0.27 in this case. So it's more or less the same value. So it's a slightly lower activation energy here, which does not seem to correspond to that the electrodes are playing some role. Oh, well, it's still very controversial. And then, as I mentioned before, I took these images from literature, from a paper from Sean Bishop, as I mentioned before, that they are working in this very interesting optical absorption fast response of the materials. So most of these materials, or some of these materials, because the electronic configuration and the electronic carriers are changing in relation to the changes in the oxygen stoichiometry, there could be some variations in the optical response. And in this particular case, for this material, there is an interesting, important differences between the reduced material and the oxidized material in the visible range. So one can monitor this optical response at a single wavelength, so we can follow the transitory changes upon oxygen pressure variations, as is being observed in these graphs. This is interesting because it can be acquired very fast. Important because it does not use any contact, so this is a very important thing. And again, it's an average value of the film, but of course it needs that the film is transparent and the substrate is transparent. So it could be some limitations in some cases, but it's a very interesting thing, very complementary to the other techniques, particularly because it does not use contacts as in the case of conductivity relaxation experiments. And then I come to this technique, which is the one that we are using, we are exploring very recently, and it's taking advantage that some of these materials, they change the structure when oxygen incorporates or goes out from the structure. In this particular case, this structure incorporates oxygen in interstitial sites. So these oxygen interstitials, they affect the volume of the cell. So once you increase the oxygen content, the cell expands, and when it reduces, it compresses. And it does it in a particular way, so it's a bit anisotropic. So when it incorporates oxygen, it increases when it incorporates oxygen, it increases the C-axis parameter and reduces slightly the AB parameter, whereas as the opposite when it reduces. And if we work with thin films, those are mostly epitaxial films, so the AB axis is almost restricted. It's very much attached, very stiff, attached to the substrate, so it does not vary very much. And all the volume changes are taken by the C-axis, which is free to expand or contract. So this X-ray diffraction is a very powerful technique to analyze the structure. It can analyze very slight variations in the cell parameters. Here, there is a kind of representation of the reciprocal space map, which is what X-ray diffraction really measures in the structure of your material. So you can have, in this reciprocal space, you have spots coming from the substrate. These reflections, they give you a very accurate measurement of the cell parameters of the substrate. And you have other spots that gives you information about the film. This is the film C-axis parameter. So if the film changes the C-axis parameter, this spot moves along the vertical direction in the reciprocal space too. So for instance, for under nitrogen atmosphere, the material has reduced, so the C-axis parameter has become small, and in the reciprocal space, it's just the opposite, and it goes up. And when you heat up in air, then this value of the C-axis parameter, it's larger, so it has become to a lower position. So this is very subtle here, but by X-ray diffraction, you can analyze this with a lot of accuracy. And which is very important in this case is that the measurement of this reflection gives you information of what happens to the film structure, and nothing related to the substrate. So it's totally selective to what happens in your film. So one of these maps, it takes some time to be recorded, to be measured, but you can, for certain reflections, you can have in a simple 2 theta detector scan, you can go, if you are in a particular reflection which is very asymmetric, you can perform almost a vertical scan. So it follows perfectly the C-axis variation. And this you can do it very fast, but with an X-ray diffractometer. But the one we use, it has a new type of detector, which is a linear detector. So it has different channels. So you don't have even to move the detector. You have the detector in a fixed position. You have 255 channels, and you explore a range of 2.5 degrees, which is enough to give you a snapshot of your structure. So this is what we have. We can acquire this with a very nice statistic, very low noise, and time intervals as low as 2 seconds. Sometimes, depending on the film, if the film is too thin, then you need more time. So this is the substrate reflection, and this is the film reflection. So one can see that we can measure every 10 seconds, I think, in this case. Every 10 seconds, you can have one of these scans, so you can follow very nicely the variations under the change of oxygen pressure from air to nitrogen. So we can do cycles from nitrogen to air at different temperatures. This is at high temperature all the time. So you can follow very nicely the variations in the structure. So one thing which is interesting is that the accuracy of the measurement, if you see here the figures, it's, you can measure below the 1,000th of an angstrom, which is an impressive resolution. So you can monitor changes with about 10 ppm variation, so which is 0.1 picometer. And this well, allows you very well to follow this oxidation and reaction dynamics. So then we analyze what happens in this transitory at different temperatures. Okay, we can do that at different temperatures. So we have, by increasing the temperature, you have increased Z-axis parameters. So this is related to thermal expansion, but also we can have the chemical expansion, which relates to the variations in the oxygen content in this material. This is very interesting for these cathode materials, but of course it can be used for any other kind of materials where you are interested to know the chemical expansion and of the material. But I forgot to say that for having this kind of maps, you need the film to be epitaxial, so very highly crystalline, which is mostly what we are interested in this kind of analysis. And then you can analyze the kinetics, so you can perform fits to extract the information about these dynamics. And we observe in this case, well, it's in a logarithmic plot against the time, and these curves, they correspond to a double exponential decay, well, double exponential increase in this case. So the best fit, again, corresponds to a double exponential, as in the case on the conductivity relaxation. So it's an indication that, again, we can have a fast process with related to the oxygen surface exchange, and then a slow process that now we can say that the slow process does not have anything to do with the substrate, not even to the two-dimensional conductivity or surface conductivity of the film. So it corresponds to a part of the film. So it's a certain volume of the film, which is really evolving at a very slow rate. So it means that, okay, we have to look what happens in our films. It's probably related to something which is present at the interface with the substrate, and probably related with the strain which these films have in the, close to the interface. For the reduction curves, we can observe quite a similar response, quite a similar decay, which is also can be fit by two different exponentials. For the fast process, we can say that it's again thermally activated, but for the slow process, it seems to be much more complex, and it's quite tricky, and seems to depend on the sample history, and it gives us an additional complication, to measure these films. So here, for instance, we can have one film measured at 700 degrees, several cycles, up to 7 cycles, and you see that progressively, under nitrogen, there is a reduction of the Z-axis parameter of the film, and when you oxidize, again, it does not recover the full values. So this is related to the slow process that we mentioned before. And we can be sure that after this kind of experiments, we have not reached the stationary level. So we could only reach this level once we go for very, very long experiments. And we have performed experiments that run for hours, and we still have a drift of this Z-axis parameter. So it means that this interfacial layer is much thicker than we expected, or it is maintained for very long time. So this gives you an additional difficulty that when you measure the absolute values of the Z-axis parameter or the absolute values of the conductivity on these films, the profile of your oxygen content in the film, it's very dependent on previous history of the sample. So this is something that has to be taken into account. And we perform very analogous experiments by conductivity relaxation, and we observe exactly the same thing. So the conductivity after several cycles between nitrogen and oxygen, in nitrogen, it was reducing all the time, and it was not recovered. In this case, we thought it was a kind of degradation of the film, probably generating another different phase, but the fact that we are measuring this by X-ray diffraction, the same reflections, indicates that it's still the same or related to the same phase of the material. So what we think is that at the interface, there is a region which the defect chemistry is affected by the substrate. So it's either spinned by the substrate. So it does the equilibrium. It does not reach the equilibrium conditions with the atmosphere. So it probably has another different conditions which are related to the electrochemical potential of the substrate. So whenever you change from oxygen to nitrogen, there is still this region which evolves in a different way as the rest of the film. So this has to be taken into account if one wants to work with very thin films, because imagine that these films were thin enough that will probably the oxygen content will be determined by the substrate and not by the atmosphere. So this is something that we are very keen to prove with very thin films, if we are able to stabilize other oxygen content or change the dynamics of these films. And well, this has also evolution with the cycling. So whenever you use different cycles, then especially at low temperature, it seems to evolve very much. Not only the fast step of the oxidation or reduction, but also the slow step is also very dependent on the history. So this is something to take into account. But still, at high temperatures, we are able to extract information about the fast oxidation process. And it was very surprising that the values that we obtain for this from this method are exactly the same as those that we obtain by isotopic exchange. So this, we trust very much that we are doing we're doing the things properly, and the activation energy also surprisingly comes to exactly the same values as from isotopic exchange, at least for the oxidation step. For the reduction step, it's a different thing, and we have much larger activation energy, which indicates that maybe there is a different mechanism taking place in the film reduction. And of course, this is also interesting because once you have a material which is combines two different materials, like a bilayer in this case, is a coupling lanthanum nickel 04 and lanthanum nickel 03. So this is a perovskite, and this is a like a Rudolph-Popper phase. So we have grown these bilayers, and you see this is a reciprocal space in a selected area of this bilayer. So we can have reflections which corresponds to one material and another one to the other material. So we can separately, selectively analyze what happens to the top layer and then to the bottom layer. So this is interesting not only for these kind of heterostructures, but maybe also for composite materials, which then we will be able to extract the kinetics of both separately. And what is very nice in this particular system is that once you oxidize from nitrogen to air, lanthanum nickel 04 increases the Z-axis parameter, whereas lanthanum nickel 03 compresses. And this is, I mean, what you expect in this material from the defect chemistry. The main defects in lanthanum 2 nickel 04 are oxygen interstitials. So the oxygen, when it incorporates, it increases the volume of the cell. Whereas in lanthanum nickel 03 is a perovskite, it's typically oxygen vacancies on it. So when you incorporate oxygen, you have less oxygen vacancies. So the volume of the cell reduces. So it's a very nice heterostructure because you have this opposite reactions. So we can follow those two layers independently. So what has been interesting in this case is that, okay, we could extract oxidation and reduction kinetics of both materials. So we were interested in knowing if one affects the other, because this could be interesting if you want to make like active layers for a better performing cathode. And well, in this case, we observed that oxidation surface exchange rate or time response for the oxygen incorporation, it's more or less the same time for both materials. So it means that once the oxygen incorporates into the top layer, then it immediately is felt by the bottom layer. So the oxygen crosses without problems to the bottom layer, which means that there is no problem, a diffusion problem at the interface, at the solid-solid interface, which is interesting because it's very difficult to measure by other techniques. In this case, we can analyze these kinetics, not only the surface kinetics, but also the interface kinetics. And what we observe that is also interesting is after several cycles, lanthanum 2 nickel 04 reduces the Z-axis parameter. That means, okay, it means that it loses oxygen after cycling, whereas the perovskite, lanthanum nickel 03, it reduces the Z-axis parameter, which means that it gains more oxygen. So it's an interesting case because it seems that cycling makes the oxygen to go more and more towards the bottom layer, which can have a particular use in some kind of devices. But we are more interested in the fundamental studies of this kind of heterostructures. And then I come to the last of the techniques that we are using. Is, as I said, is electrochemical strain microscopy. It has been mainly developed at a group in the States, in Oak Ridge, and also in combination with some AFM producers. And it consists of AFM tip, which is a conducting tip, which is in contact with a material that we want to study. And then this tip is placed, there is a voltage applied to this tip, an AC voltage at a high frequency. So you can induce an electric field and very locally under the tip. So you can make the carriers, all the electrons and ions, all the mobile species in your material to migrate towards the tip or against the tip. So for some particular materials, the change in the ion concentration will make variations in the structure, as we saw before. So very locally, we can have a variation in the surface topography of the film. And okay, one would say that this is very, very small. But if one works in a particular frequency, which is a contact resonance frequency, this can be enhanced. So there are some displacements that can be monitored by the AFM and are in the range of picometers. And they are not related to the electronic charges. They are related to the ionic charges, those causing volume changes in the material. So it can be related to some electrochemical reactions locally in the film. So this is very important because there are very few techniques which can explore locally what is happening in these materials. This has been successfully demonstrated for lithium ion mobile materials, cathodes and electrodes. And also, well, this is kind of a very complex type of dynamic measurement that you can map. You don't have a simple topography signal of one dot in your material. You can perform a full spectroscopic analysis in each dot. So you can make an array of dots onto your surface, so you can explore the electrochemical activity over the surface of your material. So you can correlate this with any feature in your topography, like grain boundaries or some other defects in your topography. So this is what is powerful of this technique. And this is room temperature analysis. And even under room temperature conditions, it has been proven in YZ, this is an ionic conducting material with some platinum dots onto the surface. It has been observed that the electrochemical activity in this film, this is overlapped with the topography image. So those the red spots that we observe corresponds to the larger electrochemical activity, so which is this hysteresis curve when it becomes larger. So this indicates that the activity takes place in the region where coexist the YZ surface and the platinum surface, which is exactly the triple phase boundaries where we expect this the main oxygen incorporation in these materials. And this is room temperature, but still, by the use of these high electric fields on the order of from 2 to 10 or 20 volts, it's still possible to let the ions to migrate and perform in similar way as it would perform at high temperature. So this is interesting to see if this works as a technique for also analyzing other type of mixed ionic electronic conductors that we use as cathodes. And presently we are working in this material, barium strontium cobalt ferrites, which is a very also a very interesting low temperature cathode material. And we are performing this kind of analysis. It's a bit more tricky in this case because it's not insulating, it's a semiconducting material, so it has a certain conductivity. So we have to use, I think it's not very clear here, we have to pattern some small regions in the material so we can be sure that we only analyze this part of the material. Otherwise, the electric field is spread all over the cathode. And we can perform, well, we can analyze these hysteresis curves, and we can analyze different features of the hysteresis curves, which have been correlated with the presence of different phases in the surface. when one works with AFN, one has to be always concerned about if the things that are measured are not related to the topography of the films. And in this case, there is a particular way to measure to totally decouple the possible crosstalk effect of the topography in the signals. So when you see some contrast here, it's not related to the topography. It's related to the different phase, to the different electrochemical activity of these phases. So this is interesting to localize some particularly more active areas in your surface, and then to focus on how to make the films to have an average, more performant activity. And just wanted to end with some conclusions. It's just a summary of what we have seen, is that all these techniques, although they are different, they can be very complementary. Particularly this X-ray and conductivity relaxation and isotopic exchange, they can give you this average K values. Particularly X-ray diffraction is very selective. As we saw, it can measure different materials and different type of interfaces. And this electrochemical strain microscopy is one of the few local analysis tools that one can use for exploring these electrochemical reactions. Of course, one has to try to implement this electrochemical strain microscopy at higher temperatures to see if it's more closer to the working conditions. We can work with polarized structures. We're working in the real fuel cell operation, close to the conditions of the real fuel cell operations. We can analyze if surface decoration can enhance the catalytic activity of the films. And this is what we have been doing in the past, and we will be doing in the future. And well, I would like to thank you for your attention, and thank my person of the group. Some of them, Andrea is already left. He left to Imperial College. So everybody is leaving to Imperial College. I don't know why, because the weather is not particularly interesting there. But probably there are other things which are appealing there in London. And I just acknowledge also the funding of this work. And thanks very much, Professor Ishihara, for having invited me to give this talk and the opportunity to be here with you and get to know all the country. Thank you very much.